this is 2 to the x. I tried to type it, it didn't look very good. So this is 2 to the x. The exponent is our x variable. And I want to do this just like we have every other graph that we've done. We've always started with -2, -1, 0, 1, and 2. And why did we always start with those values? Well, not that small, but what is that? What is the -2, 1, 0? What do those represent? Stuff on both sides of the axis. Grab 2. Sorry, I just realized I forgot to hold this, so I apologize. Well, you know what? This one's not bad. These aren't bad to have some graph paper with. It does help a little bit. But yeah, grab a couple of them. And I'm sorry that I did forget about the hole punching thing. It's back here. If you bless you, if you do want a hole punch, I'll just send it around and you guys can help out. Not literally, but figuratively. All right. So remember what this is doing. What is anything to a negative exponent?
1 over.
Okay. So if it's 2 to the -2, what does that equal? 1/4. So that's 1/4. 2 to the -1. 1/10. What's anything to the 0 power? 1. What's anything to the first power? Itself. Good. And then this equals 4. So for rough ideas here,
Nothing. I just don't know what to do with this now.
pass it to somebody else and like the hole puncher. Oh, let go. And then just start plotting some points. Now watch what happens. At -2, we said it was at a 4th.
Yes.
Then it's at a half. Then it's at 1. And then it's at 2. Now, what happens if it's 2 to the -3rd? It's an 1/8, right? And then it'd be a 16th, 32nd, and so on and so on. Will it ever cross that the x-axis there? It's going to get infinitely closer and closer and closer to it without actually touching it, because you can get a number smaller, continue to get smaller. So your graph will look like that. Okay. Now, take your calculator out real quick. And I'd like to go to my y equals table. Sorry, I got to clear out all my stuff. And I'd like us to put in 4 graphs. I want to go 2 to the x, 3 to the x, 4 to the x, then 5 to the x, and hit graph. Okay. What do they do?
They shoot up.
They get steeper with the higher the front, the number in front, don't they? Okay. What do they all pass through? The y-axis. Where's the y-axis? X equals 0, but when x is 0, the exponent is 0, which makes the y-intercept 1. Okay. So what happens here is that we get these kind of the same general idea here over and over again, which is going to allow us to do some basic things. We just did this. Oops. Did it ever cross the y-axis? Sorry. The x-axis. No. All right. So what happens is we have this thing called a parent function. And we've talked about parent functions before. Excuse me. So we have this thing where we call it y equals b to the x. And again, there's not a really easy way to type this into the smart board with an exponent. So think of it that way. Where b is greater than 0 and it is not equal to 1. B is always greater than 0 and it's not equal to 1. Because if it was equal to 1, everything would just be 1 and be linear. Okay? Because 1 to any power is always going to be 1. So that's why we say that. Now, what this allows us to be able to do is when we have these things called exponential graphs, exponential functions, if you will, is that we get this bit of information. We can figure out what the x-intercept is, what the y-intercept is, where's the horizontal asymptote, what's its domain, and what's its range. So going through these things, y-intercept is what? I mean, how do you find a y-intercept? Where is that located? And when x is equal to 0 for the parent function. Yeah, we'll be able to do all that. Will there be an x-intercept with this parent function? No, it's not going to cross the x-axis. Remember the x-axis is the one.
Oh.
Yeah, the x-intercept. So the y-intercept is when x equals 0. The x-intercept does not exist. Which means there's a horizontal asymptote. In this case, we're going to have a horizontal asymptote at 0. At y equals 0 will give us a horizontal asymptote. Looking back at that graph, the domain goes for possible x values, range goes for possible y values. Was this domain restricted at all? Look at your graph again. Think about the graph. When I go back to that graph, is that domain restricted at all? Can I pick any value of x? Yeah. So the domain for these guys will always be all real numbers. The range, on the other hand, is basically going to be what side of the asymptote is this graph drawn? Is it above the horizontal asymptote or can it be below the asymptote? And this graph that we did a second ago, excuse me, it was above it. So we would say that it was all values of y that are greater than 0. Okay. Range goes with the y values. Domain goes with the x. All right. I don't mind it. It's not the end of the world. Well, this is when you say all real, it's just going to be all real numbers. So, I mean, if it was measured, it wouldn't work. Not terrible. Pretty straightforward. Which then allows us to do this. That should look familiar.
Oh, yeah.
What did the H stand for again? Remember? You just said it. Horizontal. Your H value was your horizontal shift, and your K value is your vertical shift. H goes left and right. K goes up and down. What values go left and right on a graph? X's. What values go up and down on a graph? Y's. What letter comes first in the alphabet as you're in between A or a, between an X or a Y? What comes first in the alphabet, H or K? H. It's the It's those little subtle things that if you keep remembering that H corresponds to the X, K corresponds to the Y. Horizontal, vertical. It's stupid. You won't forget it because you'll keep thinking of me of saying vertical. All right. So this idea here of what A, H, and K will do, A is like a scalar. Think of it as a scalar. It's a multiplier up and front. If it was written as y equals, I don't know, 2b to the x. Oh, I need to get the base value. If it was 2 times 2 to the x, order of operations tells you what to take care of first. The exponent, right? And then you have to multiply it by 2. This 2 value is just a scalar. It will increase it or slow it down. It might invert it because it could be negative, things like that. That's all that means. Right? Just think of it as order of operations. Your H is the horizontal shift. And the K is the vertical shift. And what we're going to do is, as you guys know, I'm not a huge fan of using graph paper a lot, but with these things, using graph paper makes a lot of sense because you're able to plot what we call a parent graph and then shift the parent graph, the H and the K. And that's the easiest way to do things. Plus, you'll also get used to seeing this idea of parent graphs as we get further along when we do logarithm graphs next week. And then in a couple of, about a month, when we start graphing trig functions, we'll graph the parent function of a trig value and then shift that as well. Okay? So there's a lot of the idea of parents and their shifts. So just want to get this out of what? We're really excited about graphing trig, but I'm not being able to. I hope you guys have questions and flexes. I'll come and help you. Love trig. My favorite. I don't know. I don't know, it's like sine and cosine. So let's try this. So we have, what I want to do is horizontal asymptote. Excuse me. X-intercept, if there is one, Y-intercept, and then we're going to graph it. But whenever we graph these things, what we always do is we're going to label what are the A, H, and K. What are the A, H, and K values here? This idea of labeling this first, you're going to see this a lot. You're going to ask, what's the A value, what's the H value, what's the K value? Now, we're going to be able to figure out bits and pieces, okay? In this case here, what's the A value? It's a half, good. So your A value is 1/2. What's your H value? 0. There isn't one, so it's 0. What's your K value? 0. So by there not being an H or a K value, that tells you that your horizontal asymptote is at 0. The horizontal asymptote is at y equals 0. If there was a K value, guess what it does to the horizontal asymptote? Correct. Which means that your horizontal asymptote will always be located at your K value. Very good. Horizontal asymptote will be located at your K value. Now the H value being 0 just means it's not being moved left or right. So when we go to graph something like this, we can kind of piecemeal it together rather easily. If I say 3 to the negative 2, that's 1/9, right? What's 1/9 times 1/2? 1/18. So let me shrink this just a little bit. So if I say it's at negative 2, that gives me 1/18. If I say it's at negative 1, what does that give me? What number is that? 1/6, very good. It's 1/6. If it's at 0, what is it? 1/2. At 0, it's 1/2. Oh, that's helpful, isn't it? That means where is your y-intercept always going to be at for your parent function? Well, it's x equals 0, but when you substitute in for 0, your y-intercept will always be at your a value. Your y-intercept for your parent function is always at a, because then it can move left or right, up and down, depending on what the shift is. But your parent function, your a value, gives you your intercept. Okay. When I go 3 to the first power, what's 3 to the first power? 3. So then I would get 3/2. You okay with that? And if I do that again with 2, I get 9, which is 9/2. You okay with that? All right. Now, even though these are fractional values, we're just kind of getting an idea of close-ishness. 1/18, well, that's small. 1/6, that's a little bit bigger. 1/2, I could find that. 3/2, well, that's how much? 1.5, I could find that. And then 9/2 is how many? 4.5. That's findable on a graph, isn't it? Now, this is why I don't mind using graph papers for some of these, because you're looking at halvesies. Will you get some of these crappy looking 1/8, 1/16 and things like that? Yeah, but they're not terrible. It's not like you're having to get a measure out with a little micrometer and figure out exactly perfectly where it's going to be placed. You get the general idea. Okay? And you just make a curve. Micrometer is a measuring device. Actually, no. I'm sorry. Micrometer wouldn't help you with this. Micrometer helps you find thickness, wall thickness, or how large something is. You ever seen the tool that? Actually, I think I have. Of course, I think I would. So anyway, what a micrometer does, think of it as if you take your fingers like this and spread them out, it actually has a gauge to it to measure the interior diameter of a pipe or the exterior diameter of something. It's mainly used for tubing, if you have to figure out diameters of piping and all that. If you're doing plumbing pipe, that's really, you don't have to worry about that because half-inch copper is half-inch copper. It's the inside diameter is measured. If you're doing PVC piping, like the white piping, you see the drain pipes in your house. If it says 4-inch, it means the inside diameter is 4 inches. But when you start getting into like cars, or if you're starting to look at fuel lines, or you're trying to build something out, you would use a micrometer to figure out the interior or the exterior dimensions of the tubing so that way you can get the right fittings so you can solder them together. That's where you get micrometers. It's a measuring. Soldering, you take copper, you know what copper pipe looks like, right? Water lines. When you have 2 copper pipes, you have to take what's called a coupler. It goes, if you ever look at your piping, there's a piece that goes over. Where there's 2 are joined together, what you do is you take sandpaper or something like that, and you rough up the edges to take some of the oxidation off the pipe. You put this material on it called flux. You heat it with a torch, and then you use what's called silver solder. The silver solder has it's a high melting point, and it takes the flux, cleans it, and when you heat it, the solder gets sucked into the fitting, and it welds it, and it makes it solid. Whereas if you have, maybe you guys have plastic, like that cream colored piping in your house. It's called CPVC. I know it's legal in DeKalb County that you can use that for plumbing stuff. That's the same idea when you've seen all the white drain pipes you have in your basements or whatever. You ever notice how there's like a purple color around some of the fittings that you might see that might be past it? That's the glue, the primary glue. So it's instead of gluing it together, you have to heat up the pipes and do all that. Soldering's fun. Anyway, bless you. Once again, there's not a lot that my brain doesn't know about, so. All right, same idea. Biology I'm no good at, but get me like, soldering, I can do all that stuff. I started framing stuff in my basement this weekend, it's good times. Got busted out my nail gun, it was awesome. You ever used nail gun? It's great, it's just fun. Well, yeah, this is a little bit different. I mean, you could shoot the nail gun if you really, really took off all the safety equipment and just sat there. At that point, just get a BB gun. Right. True. Anyway, what's your A value now? Your A value is -1. Good. So where's your y-intercept going to be? Your y-intercept will be at -1. So we know right away that my y-intercept is going to be at -1. Huh, we haven't done this version of this yet. Is there an H or a K? No, so there's no horizontal and vertical shift. So where's your horizontal asymptote? Horizontal asymptote is at 0. So these guys are both zeros. A is -1. So y equals 0 is your horizontal asymptote. Our y-intercept is at -1. And then again, start walking through your mind about how you work with these values. Well, if I use -2, 3/2 to the -2 means I'm flipping the fraction and squaring it. 4/3. Multiply that by -1, you get -4/3, or 4/9, sorry. Okay? So if it's at -2, we flip it, square it, and multiply it by -1. If it's at -1, I flip it, I get 2/3, and I multiply it by -1, and I get -2/3. At 0, it's -1, because anything to the 0 power is 1. 1 times -1 is -1. 3/2 to the first power is 3/2. Multiply that by -1, -3/2. And then again, 3/2 squared would be 9/4. 9/4 times -1 is -9/4. Remember, the numbers that we're selecting aren't terrible. By continually using that -2 through +2, you get a nice range. You're going to see everything that's happening around the y-axis, and you can plot stuff through. 4/9. Is that more or less than or pretty close to half? Pretty close to half-ish. So at -2, it's almost -1/2-ish, somewhere like there, I guess. 2/3, a little bit past a half. -2/3. And then I'm at -0, -1, 1, and then that's what, 2 1/4. Okay. So the difference here, we got to put our asymptote in. The difference now with this graph is that it's still an exponential growth one, but it's negative, just reflected over the axis. It just goes a different direction. You'll know right away if your points aren't matching up to make these nice curves, you done goofed. Okay? You done goofed somewhere, and you probably just missed up a sign. All right. Try one with an H and a K. See how we do. There we go. Try with the H and the K. When we do these, we're going to do it in 2 steps. We're going to plot the parent function, and then we'll shift everything. That's the easiest way to do it. Okay? Plot the parent, then shift. Because when you look at this, we have, let's see. Our parent function for y equals 3 times 2 to the x minus 1 all minus 4. What's the parent function for this? No, remember, your parent function is just this guy. Your parent function is your a b to the x. Okay? That's always going to be your parent function. So I know my parent function would be y equals ab to the x. Well, what's my a value? 3. Now, our h value, remember what it said, x minus h. Very good. Yep. Your h value is 1. What's your k value, though? -4. You guys remember the representation when we did h's and k's? It's usually minus h plus and k. Same idea passes here. Same thing, right? So that means our k value is -4. That tells me for every point that I plot for the parent function, I have to move it to the right 1 and down 4. Okay? Does that make sense? It's the easiest way to do these things. That's why we plot our parent functions. So you start. We know that if I use the parent function through -2, -1, 0, 1, and 2, 2 to the -2 is 1/4. So it's 3/4. Okay with that? 2 to the -1 is a half. So it's 3/2. Always. Yep. Always go parent function because then you shift out of that. It's the easiest way to do it. Otherwise, you start worrying about all these order of operations. It just gets to be too messy. It's not worth your time. This, all right, you know what? This might take 15, 20 seconds longer, but it's hard to screw up. I got faith in you. What's anything with the 0? 1. 1 times 3 is? And this one becomes 6. And then 3 times 4 is 12. We okay with that? All right. Plot it. We know that our parent function has it at y equals 0. We know that we cross our y, the y-intercept is at 3. At -1, it was 1.5. At -2, it was 3/4. We haven't shifted it yet. This is the parent function. The parent function will always have it still at 0. Because think about what happens when we move it, that asymptote's going to move down. All right? So I'm going to plot parent. This is where if you've got 2 colors, it's going to be really helpful. What did I say? 1 and 6, and then 12 is up here. When you graph parent functions, we want to use dotted lines. You guys vaguely remember that? Because it's a line that's there for the purpose of us visualizing what to do with it now. Excuse me. Now that means that for every one of these points, all I have to do is move it to the right 1 and down 4. I know that we have a new horizontal asymptote. We'll be at y equals -4. And then if I move this to the right 1 and I go down 4, could I figure out what those ordered pairs are? -1, 3 1/4, -3 1/4. See where I'm going with that? To move it, you know that you're, I wish I had an extra spot there. When you have your parent function was -2, 3/4, -1, 3/2, 0, 3, 1, 6, 2, 12. Your shift was x plus 1 and y minus 4. So if you think about it, just math, this would have been at -1, -3 1/4. This would have been at 0, 1.5, so it would be what, 2.5? -2.5? This one would be at 1, -1. It'd be at 2, 3, and 8. What I'm doing here is I'm just doing the math between the ordered pairs just by adding or subtracting it. I think, did we do that with, what function did we do that with, where we added and subtracted stuff in the ordered pairs? Do you remember that? Was it a quadratic one? Remember where we added, we just relisted the ordered pairs, we just added? Yeah. Oh, that was with the conic stuff. Where we took their stuff, we just added the H, we added the K values, but it was A's and B's. The same basic idea, where you have your ordered pair, you're just transferring the ordered pairs to a new set. Right? That's what we're looking at being able to do. Can you take and figure out where your shift was, apply it to your parent graph, relist it, and plot? That's it. So what did I say out there? 0, -2.5. Oh, that's one. -1 and 1. 2 and 2. And then 3 and 8. And hopefully your graphs are going the same direction. Because if they don't, you're not good. That's right. The whole idea here, guys, is can you take your parent graph, transfer it. Okay. You take the parent graph and transfer it. So as of right now, everything that we've done, our B values we've had were all greater than 1. I don't know if you noticed that. Those are exponential growth problems. Exponential growth has B values that are greater than 1. Exponential decay have B values that are between 0 and 1. So if you want to look at something like that, since we're running just a little short, doing this isn't any different than anything else. I just realized that. Take your calculator real quick. Just type in the y equals table. Do an alpha y equals. We'll do a fraction of 1/2. And then we'll do that to the x. It's just going the other direction. Exponential growth goes left to right, or left to right going the other direction, pointing downward. Exponential decay goes the other way. It's just the other direction, which means if it was a negative, it had an A value that was negative, it would just reflect it. That's all the negatives do, it just reflects it over whatever you're asking for. Everything else is the same. Everything else is exactly the same. How we set our parent functions up, how we set up the shift values. Just listing out 2 sets of ordered pairs is the easiest way to do all this. And that's what we're doing. So decay, growth, has a B value that's greater than 1. Decay, your B value is smaller than 1, but it's bigger than 0. Right. If there's an A value out front, that just gives it the scale. The A value for both of them will always be the intercept, your y-intercept. Yes, sir.
What if B is less than 0?
It won't work. Because if it's less than 0, that means your A value is the negative. You'd have to encompass it within the parentheses. Growth and decay are always going to be, your B values are always positive. See what it works. All right, I'll show you one. Same idea here. When you have a fractional exponent, if you raise a fractional exponent to a negative power, remember all you're doing is flipping it. So 1/2 to the -2 would be 2 squared. 1/2 to the -1 would be 2. Does that make sense? Is it vague to bring about? Again. Your A value, or sorry, your parent function here is y equals 5 times 1/2 to the x. Is this a growth or a decay problem? Because what if it was 3/2? Yeah, that's, and I'm thank you for saying that, because that people will say that all the time. What's a fraction? It's got to be k. And then I just automatically say about 3 halves. So that's good. If the b value is smaller than 1, but bigger than 0. Okay. So here your a value is still 5. We had no h value. We had a k value of 2, which means when we're done shifting everything, where's your new asymptote token? It'll be up 2 because it's a positive 2, so your new will be there. When you're doing your parent function, what's that? Yeah. Yep. So when you do your parent function here, excuse me, you're still picking your -2, -1, 0, 1, and 2. But again, when it's 1/2 to the -2, it's unhappy. Flip it. Just becomes 4. Okay. So you get 20, 10, 5, 5 halves, and then 1 4, 5 fourths. Okay. You would plot those parents, and then you would go ahead and shift everything through, right? I threw in 1. What's 1/2 of the 1? There you go. 1/2 times 5.
Yeah, I got it now.
You plot the parent, and then you plot the shifting thing. And when you do your shift, remember how I wrote it up? You always start with your parent, and then you would plot your shift as well. So with these things, I know I kind of didn't do enough with the decay, so we'll just try a couple of them. So there's 2 sections in the text here. On 8.1, let's do. We'll try those 6. Same idea. Label everything, plot, parent, and the shift. If it's easier, I would suggest writing out your parent function, your ordered pairs for your parent, and then put your ordered pairs together as far as the shift is concerned with your H and K and relist them. It's easier on your brain for most of you guys to see what math you have to do, because if you replicate this, you guys should like to do math that you have to replicate without having to overthink it, it will be easier on your brains. Okay, so I would do it that way. Tomorrow we'll get into a little bit more of this. I know we didn't talk a ton about decay. We'll try a couple of those, see how you did. We'll introduce what the exponential one does. We'll just kind of go from there, see how we do. Okay? Not too terrible. There's a lot going on. If you need extra graph paper, I got plenty of it still. I think with the 6, that you should be able to knock that onto one of your sheets. It should be all right. We're wrapping.